Hey guys, I want to talk to you today about Pascal's law, and Pascal's law states that if we apply pressure to a fluid, that pressure is going to be dispersed evenly in all directions. And so it's very useful in something called hydraulic systems. So we can use liquid to under pressure, and if we apply force to it, that force is applied in all directions. So if I push on this piston here, and if I push down, if I start to put some pressure on this fluid, the fluid basically has nowhere to go but through this tube, and then since this other piston is movable, as I put pressure on this fluid, that pressure is transmitted, it moves. I'm going to move force from here to here, and that's going to allow me to do some work. It's going to allow me to move a load up and down. So it's very useful in raising a car. If we're talking about like a backhoe or something, moving dirt, so we can transfer huge amounts of force to lift things and to help us out in life. Hey guys, talking a little force, pressure, and area today. I know we covered some of these concepts in the mix and flow of matter, but that was all the way back in September. So we're going to do a quick review of that in today's class, and maybe look at some other applications of that. So we talked about this formula earlier on in the year. Pressure equals force divided by area. So if we can apply some force over a certain amount of area, we can exert something called pressure. And so yeah, we do have that formula, pressure equals force divided by area. And so force is measured in newtons, area is measured in meters squared. There are different units of area, but as it relates to the Pascal, it is good to keep in mind that when we calculate pressure, we always want our units to be in meters squared, even though there are other units for area like centimeters squared or kilometers squared. And when we're dealing with pressure, we're dealing with meters squared, square meters. And so for pressure, our units, we could say they are Newton per meter squared, but this is also equal to a unit called the Pascal as well, represented by PA. So just in a review example, if we have an area of a snowshoe that's 0.2 meters squared, and the area of your boots is 0.05 meters squared, how much pressure are you exerting on the snowpack when you're wearing boots? So to do something like this, you want to start off with your formula. Pressure equals force divided by area. In this case, our force there ain't no force, so I'm going to calculate my force. So I'm rough, I want to say like maybe 65 kilograms. Force equals mass times the gravitational pull, which is about roughly, let's say, 10 meters per second squared. So my force in this case is 650 if we're talking about me. The area, if I'm talking about snowshoes, is 0.2 meters squared. So as I get my pressure, I'm going to go 650 divided by 0.2. 3250 pascals. If you really want to get fancy, you could divide by 1000 and get 3.25 kilopascals. That's another unit you might run into. But maybe I'll just leave it as pascals. So this is wearing snowshoes. If I'm just wearing regular boots, I'm going to use the same formula. I still weigh that much, I'm applying that much force onto the snow, but my boots have a much smaller area. So in this case, I'm going to go 650 divided by 0.05 equals 13000 pascals. So how much more pressure am I putting on the snow when I'm wearing boots? I'm just going to go that divided by that. 4 times as much. Kind of makes sense, right? If the snowshoes are 4 times the area, I'm spreading out my weight over 4 times as much area. It's, yeah, so boots, since if I have 4 times the amount of pressure, I'm going to sink through a lot easier. So Pascal's law is saying that if we put pressure on a contained fluid, that pressure is transmitted. So that is kind of a fancy word, transmitted. Just means it's going to move. It's going to go somewhere else. Undiminished. Why did that word have to be there? I don't like it. But really, it just means that we're not going to lose any of that pressure. None of it ain't going to go down, and it travels in all directions. So yeah, if you think back to the example at the beginning of this video, we can use it to move a force from one place to the next as the pressure moves through the fluid. It's got to be contained though. We've got to have some walls that can also stand up to that pressure. Can't make it out of paper. Alright, let's check out this example. So we're going to apply 500 newtons of force right down here on this piston over an area of 0.05 meters squared. So let's figure out how much pressure is going to be on this fluid. Pressure equals force divided by area, 500 newtons divided by, my area is 0.5 meters squared, and that is going to turn out to be 1,000 pascals. So yeah, for every square meter in this system, there's now 1,000 pascals of pressure. And so if we have a bigger piston with a bigger area, there's a lot more space for pressure to be exerted. So this pressure is undiminished. That fancy word from before, that just means it's not going to change. It's not going to go down in this contained fluid. So if I'm looking at the amount of force on this side, I can use the same formula. Pressure equals force divided by area. But in this case, my pressure on this side is still 1,000. My force remains, and now my area is 5 meters squared. So to get force, I'm actually going to multiply both sides by 5. And what I see is that the force here is 5,000 pascals. So I'm multiplying by my force by 5. And if we think about mechanical advantage, I'm getting mechanical advantage of 5. I'm able to do 5 times the amount that I normally could. So that's how hydraulics can help us move these big loads. Okay, there's always a trade-off though, as we learned with levers and with the wheel and axle system as well. If we get a mechanical advantage, usually the trade-off is distance, and so we're going to check that out right here. So suppose we needed to raise this load in the previous example 3 meters. So if we got to go up 3 meters, how far do I have to push that piston down? So we're losing a little bit of, well, we might lose something, as we're gonna find out. So it's gotta go up 3 meters. So we're gonna use this, work equals force times distance. So, and the amount of work is not going to change. So in this previous example, the work is, well, my force was, sorry, this actually before should have been 5,000 newtons, not 5,000 pascals. I just realized. But my force was, work equals FD, my force is 5,000 newtons, and the distance I need to move it is 3 meters. So that means the amount of work that I have to do is 5,000 times 3, which is 15,000 joules. Okay, so work doesn't change. This is the work that I'm putting on the load. So the work of my effort remains the same. It's also going to be 15,000 joules. It also equals force times distance. So my work does not change. It can't. The force earlier on this previous example was 500 newtons, so I'm going to use that number. And I can use that to figure out my distance. So this is kind of like going back to our solving equations. I want to figure out d, I want to divide both sides by 500. And after I do that, I get 30. So I would have to move that small piston 30 meters in order, I'd have to move this one 30 meters in order to push this one up 3. So that's always the trade-off in all of these simple machines. If we're gaining some type of mechanical advantage, we either have to, well, typically we're moving a further distance. We have to in order to get that mechanical advantage. That's all for now.
Hey grade 8s, welcome to another edition of Doing Science the Wong Way. I'm your host, Mr. Wong, and today I'm going to be lifting up my car with one hand so I can put my summer tires back on. So step 1, I'm just going to grab underneath my car, and step 2, pull up, and I should be able to lift up this car. Here we go. 1, 2, 3. Not even close. Can't do it. With my own strength, I am unfortunately too weak. Haven't hit the weights enough this winter to be able to lift this car with one hand by myself. So I'm gonna have to use a concept from Science 8 dealing with simple machines. I'm gonna have to use a little bit of hydraulics. And so what we have over here is we got a car jack, and so what I'm going to do is there is a Shooty McFritty. So there's a tube in here that is filled with oil, and what we're going to do is put this oil under pressure by pumping this, and hopefully this will allow me to lift the vehicle so that, oh my goodness, I think it actually might be moving. It's going up. Thank you, hydraulics. Thank you, Science 8. You are the best. You're incredible. One hand getting this car all jacked up so that we can change the tires. Oh yeah. Let's get that wheel off the ground. Okay, now I got a bunch of room underneath the vehicle. That's great. The wheel is fully off the ground. As you can see, we are able to move this car up using the power of hydraulics.